Okay, great. Well, thank you for inviting me. And I was really glad to actually see that Eddie was giving the talk before this, because he's nicely set up a lot of what I'm going to say. And because, before I even get to the next slide, the main message I want to tell you is Technosignatures is just a logical continuation of the search for life. We're on two sides of the same coin is one metaphor you can think about. And I say this because historically, the search for spectral biosignatures has come from sort of different parts of the astronomical community than the search for technosignatures, which initially was known as SETI, the search for extraterrestrial intelligence. I consider these synonyms. But there have been at times, and you may see this in the old literature, tensions between these two things. And I don't see this as a tension. This is complementary. We want to find life as astrobiologists. If we find evidence of microbial life, great, we found evidence of life. If we find evidence of technology, that's great too, we found life. The implications of that are maybe different, but the goal is the same as astrobiologists. So, maybe even more than two sides of the same coin, you could think about, technosignatures are a subset of biosignatures, where biosignatures comprise anything life can do, and technology is one of the kinds of things that life can do and that will manifest as evidence of life. And so I'm going to focus on technosignatures as a subset of the biosignatures that Eddie very nicely discussed in the last talk. And so just to say a word about SETI, SETI, the search for extraterrestrial intelligence. That can be kind of a loaded term. What do you mean by intelligence? I have a pet cat. I have chickens. They're pretty intelligent. Depends what you mean by intelligent, but they're not really remotely detectable through astronomical observatories. But maybe some other biology would be. But certainly my cat's intelligence is not sending radio signals into space. So what I have at the top of this slide, this comes from Jill Tarter. SETI, the search for extraterrestrial intelligence, is really SET-T, the search for extraterrestrial technology. Technology is what we can search for. This is why I prefer to talk about technosignatures. And then you don't really need to get into the murky discussion of what do you mean by intelligence and how do we find it. Like if life can sometimes produce technology, then we can at least think about how could we detect those kinds of phenomena using tools of astronomy. And so here's a picture. Here's a picture that Eddie Schwederman actually commissioned with UCR. And this shows the Earth with several technosignatures that we have that could potentially be detectable, if there were extraterrestrials observing our planet. So there's radio signals coming out from our planet, there's city lights, there's pollution in the atmosphere, there's orbiting satellites, and things like that. So I'm going to talk in this talk about a lot of these. I'm going to try to give you a good overview. I'm going to focus more on the spectral technosignatures. I won't be completely comprehensive, but I can post some links in the Slack. This paper right here, in fact, you can find, I'll post a link to it. It's open access, and that gives a nice overview of the full set of technosignatures. So just to start, the first efforts at trying to detect technosignatures, again, it was under the name of SETI. And even before it was called that, it was a paper by Cocconi and Morrison in 1959 that suggested that we have radio transmitters, we have radio receivers, and sending a radio transmission across interstellar distances is an effective way to do communication, and we can do this with spacecraft. And so then they posed the question, if radio waves, radio technology can be effective for interstellar communication, might someone out there be trying to signal us? And is this something we should search for? And then also the idea later, about maybe we're not detecting an intentional transmission toward us, but it's sort of a leakage, the background radiation coming from a planet. So either way, and I'll mention simultaneously, while Cocconi and Morrison were writing their paper, young Frank Drake, who passed away, fairly recently, was actually starting to conduct the first SETI observation with Project Ozma at Green Bank, West Virginia, and he looked at several nearby stars. didn't find anything, but that was the birth of Radio SETI. So between Drake's search and Cocconi and Morrison's paper, we've had several decades, over 50 years of SETI observations. The Allen Telescope Array in the upper left, the Green Bank Telescope in the lower right. It's the South African array in the lower left, and then in the upper right is the Lick Observatory. And so this kind of SETI looks at mostly radio, but also optical signals. And so I'm not going to say much more about these, but there's a lot of work done. This is the bulk of actual research and data collection that has been done in the arena of technosignatures. And if you are interested in this, there are lots of ways to get involved. Check out the Breakthrough Listen initiative. That's been the biggest injection of private funds into SETI, I think, ever. And then there's SETI groups around the world. What I will say, though, about SETI is there's a nice metaphor that Jill Tarter has brought up, is how much of this has been done. I just showed you a bunch of dishes. We've been doing this for over 50 years. Well, if you think about being in the middle of the ocean and you ask yourself the question, scientific question, are there fish in the ocean? That's a good scientific question. And so you're in a boat, and what do you have? Well, what you have is you have a glass right here. I got a glass right here. You've got a glass, and you dunk it into the ocean, and then I look at my glass and I say, all right, did I get any fish? And I don't have any fish in my glass. But what did that tell me? Well, it wasn't necessarily a bad experiment. I could have caught a fish, but it says something, about the frequency of fish in the ocean, at the place I searched, that are the size at which, my glass would allow me to be able to capture. And then you can start thinking about, well, maybe I could do the same experiment with a bigger glass in different parts, and maybe you catch a fish eventually. And so if you think about it like that, one glass's worth of water in the whole ocean is about what SETI had done. And this is what Jill Tarter talked about. More recently, Jason Wright at Penn State revised this estimate. There's been new injection of funds and a new generation of SETI researchers who have made a lot of progress. And so we're at about a hot tub's worth of the ocean. So that's progress, but there's a ways to go. But what I'll talk about now is not radio and optical SETI, but what can we do with the James Webb Space Telescope, and what can we do with the next generation of space telescopes? And I see that there's several talks about upcoming space mission, space telescope concepts. I saw Sean Goldman's probably going to be talking about this, so I won't say too much, but just every 10 years. The National Academies commission these decadal surveys, these decadal reports, and in the Astro 2020 report, what came out of this was what's now being called the Habitable Worlds Observatory. And so this is a plan to have a large optical, ultraviolet, infrared observatory that, in addition to other functions, would be, an ideal tool for being able to do exoplanet spectral characterization, just as Eddie was talking about. So we are at the cusp of doing this with the James Webb Space Telescope, and so this would be the next step after that. And I mentioned this just because what I'm going to show you next is a bunch of examples of spectral technosignatures, just like we saw examples of spectral biosignatures. And so these are signatures that maybe James Webb could detect some of them, but then looking even more forward in time towards things like the Habitable World Observatory, maybe Miracle, ELTs, and things like that are going to enable us to get to the next step, characterization. So first, let's think about, well, what are some of the ways that humans have affected our atmosphere? So this is, images of ozone depletion. And so you can see from 1971 to 2017, there's the ozone hole. And the plot at the bottom shows, ozone measured in Dobson units versus time. So you can see there's a very significant drop in ozone, and this includes future projections. So we recover ozone. This is sort of a success story of international collaboration in solving an environmental problem. But it's important to note, we're not, even by 2065, projections do not have us quite recovered yet to the 1970s level. So here is, from a paper that I led, where I've shown two different CFCs, chlorofluorocarbons. So these are the molecules that are emitted by industrial activities that were the cause of ozone depletion. And you can see we've got, there's several of them, but these two have some of the longer atmospheric lifetimes. They are greenhouse gases, in addition to contributing to ozone depletion. So you can see that with time, both CFCs increased. There's, in the late 80s, there was the Montreal Protocol. So this was a treaty that banned ozone depleting CFCs. And there was, general compliance with this treaty. And you can see that now both abundances of these CFCs are decreasing. And so we are thinking about CFCs as a potential technosignature. So we can think about like, okay, what are present day levels of CFCs? That's at least something reasonable to think about us detecting, because we know that that's where we're at now. But we can also think about higher levels of CFCs simply by, asking ourselves how much would CFCs have increased if we hadn't passed the Montreal Protocol. And so, we could say, well, maybe it would have linearly increased, and you could get to, anywhere from 2 to 5 times the abundances of these CFCs that we have today. And so this is just to think about the detectability of these molecules in our atmosphere. And so we did some calculations using a 3D climate model, and then we, with different abundances of CFCs, and then we use the planetary spectrum generator to generate the synthetic spectra. And so this is if you were to observe TRAPPIST-1e with the James Webb Space Telescope. You can see at 1, 2, and 5 times the abundance of CFCs on present-day Earth. You do get a significant contrast. Now, this is model results. Eddie did a nice job showing that the real data would be messy. And then, of course, there's the problem of you would see these, even if you saw these spectral absorption features, there's a more prolonged effort to convince yourself that this is actually from CFCs and not from some other molecules that we didn't know about, or that just have overlapping absorption bands. So but this shows that we are at the cusp of being able to detect technosignatures. If there were CFCs on TRAPPIST-1e, and we were to do long integrations just for atmospheric characterization in general. You don't have to do a specific search for CFCs. We want to characterize the atmosphere of TRAPPIST-1e, and you want to look for water vapor and ozone and anything else that's within your your longer wave bands that you can observe at. And so if we were to see these kind of spectral features, it would be an interesting anomaly. And if there were CFCs on there, it would be something that James Webb could detect. And so that's kind of exciting that something like this, which maybe at one point was really just the realm of science fiction, like all astrobiology, but we can think about doing more than radio signals. We can think about looking for pollution in exoplanet atmospheres. So another reason, you might have CFCs in the atmosphere, we don't like these, these are a pollutant to us, but maybe you want to terraform your planet. And I just mentioned this briefly as people ask about it, and I like talking to, groups of younger people because maybe they tend to be more imaginative, but in any case, this is a paper by, Marinova, McKay, and collaborators. And they just showed like, well, how much warming do you get out of different known, industrial greenhouse gases, things that you can produce. These aren't in our atmosphere from any other biological processes, but we know you can manufacture these. And you get, you see different partial pressures on the x-axis lead to different temperature change on the y-axis. And, if you really wanted to make Mars, for example, warmer, well, one way you could do it is to put a combination of those kind of gases in the atmosphere of Mars, and you would warm up the planet. Should we do that? That's a different question. I did study ethics as a postdoc, and I can post a link to that paper if you want on the ethics of terraforming. But we're just thinking about what could we detect. So if we detected a Mars-like planet, orbiting another star just outside its habitable zone, and we saw a bunch of weird absorption, from CFCs, something like this, that would be really interesting. We would not have any other biological explanation other than, these are were put there through some industrial process. And this is from this is work that Eddie has done again, where we've just got the absorption cross sections in the infrared of several different species that could be used for terraforming. And you wouldn't need very much of these to get a strong greenhouse gas and a strong detectable signal. Another one I'll mention, another example, is nitrogen dioxide. So nitrogen dioxide by itself can be produced by life without technology, but a substantial fraction of the nitrogen dioxide in our atmosphere is from technology. It's a byproduct of combustion. And so here we have satellite imagery showing nitrogen dioxide over China. On the left is, before, and on the right is after the COVID-19 lockdown. And this was largely due to cars on the road, as well as, some factories. And so, Ravi Koparapu led this paper. He sent me this image and said, like, oh, looks like we have a technosignature just based on this global experiment of what happens when everybody stopped, driving for a while. And so we looked at this and said, like, okay, if you were to have just the present day Earth levels of nitrogen dioxide, and you were to observe it, the signal, you can look in the paper if you want to have more of the nitty-gritty details. The signal is in the visible part of the spectra, not the infrared like I was just showing you. So this would not be ideal for the James Webb Space Telescope, but here we did the calculation with LUVOIR, which is sort of the precursor in a design sense to the Habitable World Observatory. And so if you had a 15-meter telescope and you're observing the Earth at 10 parsecs, it would take 600 hours to get a signal-to-noise ratio of 5. So I'm just showing this one because it's simple to understand, but there's a few conclusions you can draw from this. Well, the first one is, what if there's more NO2? Of course, if there's more NO2, the observation time goes down. But what if it's 300 hours? It's not necessarily unreasonable to think about this. I'm not saying we're going to detect this, but again, Eddie made a good point. If you find an Earth twin, we're not going to forget about the planet. So, what if, we could find some good planets, maybe with tests, find some really prime candidates. Well, doing long observations of targets of interest has plenty of precedent. Anything from the Hubble Ultra Deep Field and the CANDLE survey, have been many hundreds of hours. And we're already doing long observations of the TRAPPIST system. And so if there are targets of interest, it's not unreasonable to think about dedicating long amounts of time. And again, the point I'll make is technosignature searching is not something you have to do with dedicated observing. We're just trying to characterize atmospheres, look for biosignatures, and technosignatures are just included in that. A couple last examples I'll mention. Ammonia. Again, ammonia is something that life can make without technology, but here's some imagery showing, ammonia production rates, and these are largely correlated with areas of high agricultural production. And so a substantial fraction of the ammonia in our atmosphere is from technology, and it's non-equilibrium. It's because of the constant application of fertilizer to our farmlands. And so what's technological about this? Like, well, old fertilizer was actually just animal manure, but what is technological is the Haber-Bosch process. So you can take nitrogen from the air, combine it with hydrogen gas over a metal catalyst at high temperature and pressure, and you can produce ammonia. And doing this, as you can see in the bottom, this is what feeds the world now. We are literally eating our air. Because of technology, and without this, you could not sustain the kind of food production that we have today. And there's some other variations on this, but fundamentally, you get ammonia, you apply it in an aqueous solution, and you have to saturate the soil so that roots can uptake it, and then you get excess ammonia that volatilizes into the air. And so, we asked ourselves, okay, what if you had, large scale agriculture? Could you even think about detecting this? And so this is not detectability. This is just showing a relative intensity. present day Earth would be difficult to detect, from ammonia, as well as, there's N2O and methane that would be emitted from large scale agriculture. But a future Earth with 30 billion or 100 billion people, that's something you could potentially think about detecting. And so we call this exofarm. And what I like about this idea is the other examples of pollution, chlorofluorocarbons and nitrogen dioxide. Those are what we consider pollution, and those are problems we've tried to solve. We don't want to keep chlorofluorocarbons in our atmosphere. Maybe for terraforming, that's an application, but on Earth, it'd be better if they weren't in our atmosphere. And for NO2, we would prefer that there was less NO2, and if we could find, a cleaner way to do transportation, that would be preferable. So would a long-lived civilization have a lot of nitrogen dioxide in its atmosphere, or chlorofluorocarbons in its atmosphere if they're not terraforming? Maybe not, right? But you could do agriculture, you could do large-scale Haber-Bosch synthesis for long periods of time, and you're not dependent on fossil fuels, and you're not necessarily causing ozone depletion or anything else. So this is one of the places I'm trying to think more. What are technosignatures that could truly be long-lived across geologic and astronomical timescales? And then the final one I'll mention is Thomas Beattie has done some great work about the detectability of city lights. And so not just from surface imaging, although there's work on that by Svetlana Buruzhinga, but in this case, you could detect in spectra emission lines from high pressure and low pressure sodium lights. And I didn't show the plot, you can check this paper out. But again, this is a technosignature, and one could think about the detectability of Earth today, as well as a planet with much larger urbanization. And so today we are at the cusp of being able to detect atmospheric technosignatures with the James Webb Space Telescope, which is exciting. This takes us beyond the era of radio and optical SETI, and allows essentially the whole astronomical community to participate, planetary science, in searching for technosignatures. I'll mention very briefly, I did not, this is the Sagan workshop and exoplanet focus, but you can also think about looking for technosignatures at other scales, at galactic scales, and there's plenty of literature for that if you're interested in it. And again, it's the modern tools of astronomy that are allowing us to do quantitative, meaningful science with this. The next generation of space telescopes will enable us to actually get meaningful statistics, look at dozens of planets, and look for biosignatures and technosignatures. And we need more ideas. I didn't talk about all of them, but the technosignature science is sort of at a state of infancy compared with a lot of the biosignature science that's been done, especially when we're talking about spectral technosignatures. So this is an area where if you're thinking about biosignatures, well, think about technosignatures too. You might stumble upon some idea that could be useful, and it's not about thinking about what's the most likely thing to find. It's just thinking about what are the total possibilities, a set of possibilities based on what we know, so that when we find something truly anomalous, we're able to recognize it as such and maybe start to figure out what it might be. So that's what I have, and I'm happy to take your questions.
That's great, Jacob. Thank you. We'll look for a couple of questions here. There are questions online, which I believe you can see. So while we're looking for some questions here, do you want to take a look at some of the online ones? And I'll say, just as you answered one of my pet peeves about SETI, you call it SET-T technology. I call it SET-T-EE. It's the search for extraterrestrial electrical engineers.
Sure. Right.
Let's see, we have one question here, and then maybe if you want to do one of the online ones.
So what is the balance of private funding versus public funding for technosignatures in the great balance of supporting this type of research? And how do you expect that to change? And how do you expect that to affect the science that can actually get done about this subject?
That's a great question. I'll keep the answer brief, but if you look into the history, after the SETI effort started, there was some, congressional specific people who kind of pushed back against this. And there was a time then when NASA was not funding this, when they had been putting some money into SETI before. And, we are now in a new phase of that where several NASA programs are encouraging submissions that include, technosignatures. So I've been funded by the exobiology program, with a group twice, I believe now, to study spectral technosignatures. Some of the work I presented here was funded by that. And then Don Gelino can tell you all the programs that are supported, but that has changed. And NASA is interested much more so in technosignatures as biosignatures. Technosignatures are even mentioned in the decadal survey, I think in the appendix, but it's still mentioned as being relevant to biosignatures. But a lot of the funding for radio and optical SETI remains private, not all, but much of it. And the Breakthrough Listen Initiative pledged $100 million over 10 years, and in the second half of that now. And that's been sustaining a lot of interest in this. There are groups around the world that maybe also receive some government funding. So it's a mix, and I see interest growing. I don't see indications that NASA is going to decide they're not interested in it anymore. So I think if you're at the stage of your career where you're interested in submitting proposals, put proposals in, even if it's not a purely technosignature proposal. Do biosignatures and make technosignatures one of 3 tasks if it's relevant to what you're doing, because I think that will show NASA and the community and worldwide, if there's interest in this coming from the community, then we're going to keep doing it.
Okay, thanks. We have time for maybe one of the online questions. Did you see one, Jacob, that tickled your fancy?
Sure. Oh, there's okay, megastructures. What's the possibility of taking megastructures and so connected anomalies and transits with JWST? I think megastructures are a good thing to look for with any of the anything that's looking for transit. So with TESS, and you could search the Kepler data set even, and so what's the likelihood, who knows, but anytime you're doing transits, that's something that you could think about. So I guess what I'll say for people who maybe I didn't talk about megastructures. So one of the classic SETI papers published just a year or two after Cocconi and Morrison was by Freeman Dyson. And he suggested that, well, maybe a civilization, like ourselves in the future, would want to harness the whole energy output of the sun. Right now, the sun radiates in a sphere, but Earth just intersects, a small, solid angle of that sphere, so to speak. So the light that falls on the Earth there's sort of all this waste energy going out into space. So you could think about building large scale, essentially a spherical solar panel, a bunch of little arrays going around the sun in orbit, to capture much or most of that solar energy. And so if you were to do that, depending on how one was to construct it, it might look like an artificial structure that's transiting the star. It might artificially dim the star from what you would expect it to be. Dyson predicted you'd have infrared excesses because you'd be absorbing a lot of the starlight and then emitting infrared waste energy. And so you would see a star that looks brighter in the infrared and dimmer in the optical. So things like that. And so, yeah, we should absolutely keep that in mind as we're doing transits.